coarse type of soil. So here you can see the mold of this is constant head mold. That is one of the apparatus to perform this test. But before discussing the apparatus of this test, firstly we need to perform some calculations to prepare the remolded soil sample. That how we basically remold the soil sample. For that purpose, here you can see we have the dry density, that is 1.5 gram per centimeter cube. We must have the moisture content, that is 7%. That can vary. We just took the values by assuming that the moisture content is 7%. Then we have dia of mold, that is 10 centimeter. The dia of this mold is basically 10 centimeter. So now we need to find out the volume of the mold. But how will determine the volume of this mold? We have the dia of this mold, but now we require the height of the mold. That height of the mold will consider is from the top burette to the bottom burette. So this much distance is required to perform the volume calculation, because we'll place our soil sample within this height. So this height is 20 centimeter for this apparatus. So now we'll determine the volume of the mold, that is pi r square h. We have the radius, that is 10 divided by 2, and 20 centimeter is the height, and the volume comes out to be 1570 centimeter cube. Now how will determine the mass of soil required to fill this volume basically? So as we know that the formula to find out the mass of soil is density into volume. So we have the dry density, that is 1.5 gram per centimeter cube. We'll multiply it by volume, that is 70 cubic centimeter, and the mass of soil comes out to be 2355 gram. Now we'll take 2355 gram of soil sample. You can see here. So we have 2355 gram of soil sample. Now we need to prepare a remolded sample. We'll have to add some moisture content. How? As you can see here, we have the moisture content, that is 7%. So how we'll calculate the moisture content in grams or volume? So it is basically 7% of 2355 gram. So the 7% of 2355 gram is comes out to be 165 gram. So now here you can see we have 165 ml is equivalent to the 165 gram approximately. Now we'll add this much amount of water into the soil. So now we'll add this water into the soil and we'll mix it to prepare the remolded soil sample. So this is the soil amount of soil that is required to fill the particular volume we calculated. So this is how basically we prepare the remolded soil sample. So to prepare the remolded soil sample, we always required, we must have the density and the moisture content values. If we have the MDD or optimum moisture content value from Proctor test, then we can take 95% of MDD and 95% of OMC to prepare the remolded soil sample. So these density and moisture content values can be determined from Proctor tests. Otherwise, these values can be determined on site by using in situ methods as well. So now we need to understand that how we basically set up the assembly of this apparatus to perform the test. So firstly, we need to know these burettes. First, this burette is related to the constant head. So in this burette, the head of the water is constant always. So that is why it is constant head test. Now the second burette is related to the difference of the head. It tells us about the head difference in the water. Now the third burette is related to the saturation. So it tells us about the saturation. Now, and to understand the assembly of this apparatus, that how we assemble the apparatus, here you can see the diagram. Firstly, we'll place the pedestal. You can see here, this pedestal will place in the bottom. So now we'll place pedestal in the bottom of this mold. So after placing the pedestal in the mold, now we'll place sieve number 10 over the pedestal, you can see here. So now we'll place this sieve number 10. This is basically sieve number 10. The opening of this mesh is basically sieve number 10. So we'll place the sieve number 10 over the pedestal. Now in the next, we'll place some gravels. You can see here, gravel layer over this. So it will be up to this burette size, to the saturation burette. So the thickness of this gravel layer is up to this saturation burette. So now we'll have to visually inspect the level of the gravel. Now you can see the gravels have been placed in this mold up to the saturation burette. Now, as I told, next we'll place sieve number 30 over this gravel and then filter over this sieve number 30. So this is sieve number 30 and filter paper over sieve number 30. Now here you can see this much height is filled up with the assembly apparatus. Now we'll place the remolded soil sample. We'll place soil sample over here and we'll tamp it with the wooden rammer. So now we'll place the soil sample. Remember, we have 20 centimeter height, and corresponding to 20 centimeter height, we have the volume we calculated earlier. So we need to fill that volume with this much amount of the soil. So now we have placed all the soil and in the mold, and you can see the level. It is up to this burette. And as I earlier told that we have to restrict our soil sample within this height. So this height is 20 centimeter, and corresponding to this height we determined the volume, and that volume was used to determine the mass of soil required to fill that volume for remolded soil sample calculation procedure. So now we'll place filter paper. Here you can see in this diagram as well, we'll place filter paper over here, and now we'll place sieve number 16. Sieve number 16 over there. Now we'll place some amount of gravel over there. Now our apparatus is ready to perform the test. So now in the next step, we have to add the water in the soil sample. So we can use any way to add water in the soil sample. So we have placed the mold over the sink to get the continuous water supply. And now here you can see when all the burettes are filled with the water, you can see the level of the water, and water starts overflowing from this, from here. It means our soil sample is now saturated. So now we'll perform the test. So to perform the test, we'll take the observations or readings. Firstly, we have the discharge 100 ml, that is constant. We can fix the time as well, but in our case we have taken discharge as the constant value, that is 100 ml, and we have head H1, that is 270 mm. That will be constant. That is why it is called constant head. So what we'll do is we'll check the time, and then time to fill the discharge of 100 ml, and then we'll note it down the H2 value and the corresponding temperature to perform the calculations. Now we'll perform the test. Here we have the stopwatch, and from here we'll collect the discharge from the mold, and here you can see the H1 value, that is 270 mm. The head of the water in this burette will be constant, and that is 270 mm. Here you can see. So now start. Okay. Now we'll note it down the time required to have the discharge of 100 ml. So that will be used to perform the calculations to determine the hydraulic conductivity of this soil. So we actually require the time required to have the 100 ml discharge from this soil sample.
Ready, sir? Stop.
So it means the 56 seconds, it took 56 seconds to fill the discharge of
100 ml.
100 ml. Here you can see the 100 ml, and how much the head difference is.
Now
you can see
again.
so our second burette, the value, you can see the drop of head is basically 250 from this.
From here. It's now rising up again.
Now we'll check the temperature, because temperature affects the hydraulic conductivity, and the temperature is,
when it will stabilize, it's almost 14.
so the temperature is almost
13.
almost 14 degrees. So now we'll perform the calculations, that how we perform the calculations. From the observations, we have the time 56 seconds, we have H2 value, head difference, that is 250, the H1 that was constant, the value is 270 mm, and we have the temperature, that is 14 degrees Celsius. Now let's see how we basically perform the calculations. Here you can see the trial. We have performed the one trial. Now we have H2 value, that is in centimeters. 270 mm is the H1 value. If we convert this value in centimeters, it comes out to be 27. Then we have H2 values, that was 250 mm, and in centimeters this value will be 25. Now we need to find out the head difference. So head difference is basically 20 mm, or we can say 2 centimeter, and the time was the 56 seconds. And now we'll have to calculate the discharge value. So how we can find out the discharge value? We have the volume, that is 100 ml, the fixed value of the 100 ml value, and we have the 56 seconds. So we need to find out the discharge value, that is volume per unit time, and the discharge comes out to be 1.7857 cubic centimeter per second. Now we need to find out the K value at temperature, that was the 14 degrees Celsius. So how we find out the K value? The formula of K is QL divided by ATH. L is the length of the soil sample, that was 20 centimeter basically, and Q we have calculated. Now we have area that can be calculated from pi r square. We have the time 60 seconds, and we have the H value, that is head difference, that was 2 centimeter. So by putting the values in this formula, and we can find out the K value, that is 0.00406 centimeter per second. But we need to find out the value at 20 degrees Celsius. So to convert the value of hydraulic conductivity or K value into 20 degrees Celsius, we need to apply correction. What we do, we multiply this K value with the correction, that n gamma over n20. That value can be extracted from the table that is given in the ASTM standard. You can use that table, and the value comes out to be 0.0046 multiplied by 1.165. That is basically the correction value, and the value comes out to be 0.00473 centimeter per second. So this is the value